Okay guys, welcome to part 2 of the video in which we're going to look at some more advanced stoichiometry problems, certainly more advanced than the shapes, but we're not quite to the top tier yet. That'll be in part 3. So let's look at a problem here together. I have if 16.5 grams of lead 2 nitrate reacts with excess, that's a key word there, potassium iodide, how many solid particles form? So let's analyze the problem before we even go about writing a balanced chemical equation. First of all, in this one, it straight up tells us that the potassium iodide is in excess. So that means there'll be some left over at the end of the reaction. That means that this quantity of lead nitrate, the 16.5 grams, will be our limiting reagent, and that will be the one that determines how much product can be made. Now, when we say how much product, what do we mean? Well, in this case, the question is asking us how many solid particles. So when it says how many solid particles, it's straight up telling us that we want to know the exact quantity of formula units of the solid product that is made. So this is all giving us clues to where we need to lead, and also we're going to be bringing back in our particle island from a few videos back to help us solve this problem. But first things first, let's write a balanced chemical equation. So we're dealing with ionic compounds here. We have the lead 2 nitrate, so that means the lead has a +2 charge, and if we remember, nitrate is -1, so a proper formula for lead 2 nitrate, we have Pb NO3 2. We know that all nitrates are soluble, so we'll write AQ next to this for aqueous. Reacts with potassium iodide. Potassium is +1. We see it's in group 1. Iodide is -1. We see it's in the halogen family. So our formula here is Ki. We know that potassium iodide is also soluble because all alkali metals are soluble. So we write a little AQ next to this as well. So our products here, it's going to be a double replacement reaction. The metals, lead and potassium, will switch places. So we have potassium nitrate, KNO3, because potassium, as we said, is +1, nitrate is -1. So when they combine, they'll be in a 1-to-1 ratio. It'll also be aqueous. And we have a product of lead iodide, lead 2 iodide specifically. So PbI2. Now, lead iodide must be the solid product because we know that potassium nitrate is certainly soluble because all alkali metals are soluble when combined and nitrates are soluble. So that leaves the solid product, the one we're curious about here, as the lead iodide. So this will be our point of interest here for our products. So now how do I go about setting this up? Well, step 1 is to create what I call a roadmap. We talked before about moles, and we know that here we don't have moles yet, we have grams, but we can turn it into moles. A quick reference for you is this. If you imagine a mole like an animal, where do moles live? Well, they live underground. Imagine the chemical equation being kind of like the ground, and the mole has to go down here. All the other things, be it grams, particles, or liters, those are going to go on top. So I'm going to start with the information I'm given, 16.5 grams of lead 2 nitrate, and I'm going to write that here. Now, I want to turn it into particles of lead iodide, my solid product, but to get there, there's no relationship between grams and particles, certainly not between two different compounds. We remember that from our island, but I can use the mole to relate the two. So I'm going to turn the grams of lead nitrate into moles. Then I'm going to turn the moles of lead nitrate into moles of lead iodide. And then finally, I can turn this into particles. But before I do any of this, we skipped a step. Can you see it? We didn't balance our chemical equation. So we can go ahead and do that really quickly. We know that there are 2 nitrates on the reactant side and only 1 on the product. So we're going to put a big coefficient of 2 here. That gave me 2 potassium now on the product side, and I only had 1. So we can put a coefficient of 2 here. which made 2 iodine, and we see that's already taken care of by our proper formula writing. So now we have a balanced chemical equation. So we see here also that the ratio between lead nitrate and lead iodide is a 1-to-1 ratio. So this will make this step of our problem fairly straightforward and easy. So I'm going to bring straight down what I was given and follow my roadmap. 16.5 grams of lead nitrate. And I need to turn that into moles following my roadmap here. So if I remember from Mole Island, the way I turn grams into moles is the molar mass. So I'm going to need the molar mass of lead nitrate. So I know that for every 1 mole of lead nitrate, I have to now figure out the molar mass. So we see that there's 1 lead atom here, and I look, lead has a molar mass of 207.2. There are a total of 2 nitrogen atoms here. So to that, I'm going to add 2 times nitrogen's molar mass, which is 14.01. And to that, I'm going to add the total of 6 oxygens. So 16 times 6. And we get a molar mass of 331.22 grams. The grams cancel for us, and we see that the units remaining are mole of lead nitrate. That got us to this step. Now, the next step, guys, it can be deceptive to think that this step is unnecessary. It only seems that way because in this specific example, our ratio just happens to be 1-to-1. That will not always be the case. So make sure you're doing the mole ratio step every single time. That's a common place for error. So in this next step, it's not going to do anything for us mathematically, but it will take care of the units. I can see that for every 1 lead nitrate that is consumed, and I'm going to put this on the bottom, 1 Pb NO3 2, for every 1 lead nitrate that is consumed, 1 lead iodide appears. Now, how did I decide which goes on top and bottom? Well, first of all, I want to cancel the lead nitrate, so that's one clue. Secondly, my roadmap tells me I'm going to lead iodide. Whatever I'm going to, I want to put on top. So this converts now my moles of lead nitrate into moles of lead iodide. Now there's one final step. You might think, oh, we need the molar mass of lead iodide, but we don't. Refer back to the problem. If it had asked us what mass of solid was created, yeah, we would need it. But this says how many particles. Well, to get out to particle island, we need to use Avogadro's number. So I know that if I have 1 mole of anything, I have 6.02 times 10 to the power 23 particles of that anything. In this case, the particles are formula units because they're ionic compounds. Now, why did I put that on top? Well, I wanted to cancel moles, and I know I wanted to turn it into particles. My formula unit is my particle this time, so I'm left with the units, formula units of lead iodide. That's what I wanted. So now the rest is just work for our calculator. Take a look at how I put this in when I'm using Avogadro's number so we don't get a mistake. I'm going to take my initial mass, 16.5 grams, divided by the molar mass, 331.22. That gets me to the number of moles of lead iodide. This step is 1/1, so I don't need to put that in my calculator, but if the ratio was anything else, you would want to include that here. Now I need to multiply this by Avogadro's number. So I'm going to be careful and use parentheses just to make sure the calculator is doing what I want it to. Are the parentheses necessary? I'm not sure. It depends on the calculator, but I can tell you that if you use them and tell the calculator exactly what to do, it's not going to have the chance to betray you like it wants to. So we're going to multiply that now by 6.022 times 10 to the power 23, close my parentheses, and that gives me an answer now of 2.999, so on. Now, if I want to be careful with sig figs, I know that my initial measurement had only 3, so my answer really should have only 3. I see in this fun rounding problem that the third significant digit is a 9, and the one behind it is a 9, so that rounds it up, which rounds this up. So we end up with an answer of 3.00 times 10 to the power 22 formula units of lead iodide. And that would be our final answer. So this is what a problem looks like when we know that one of the reactants is in excess. In part 3 of this video, we're going to look at a couple more examples that are a little more complicated where we're not sure which is the excess reagent to start off with. The process will be exactly the same. It just is going to be a bit more work on us. But I promise you, you'll be able to get through it if you just are very careful and diligent about showing all your work. So stay tuned for part 3 of our stoichiometry journey.